love having redundancy in our switched topology. In other words, if one link goes down, it's great to have another link standing by that can take over. However, if we have a loop at layer 2, that can cause some issues for us. The great news is Spanning Tree comes to the rescue. The Spanning Tree protocol can allow us to logically have a loop-free topology, even though physically we have interconnections between our switches that look like a loop. And if one link goes down, another link can start forwarding traffic. It's great for redundancy, but we want to talk in this video about some issues surrounding Spanning Tree Protocol. It's possible that Spanning Tree Protocol just fails on your Cisco hardware. If you joined me for the Switch Complete video course, you heard me tell the story about when I was working at Disney and we had an STP failure on a Cisco Catalyst switch, and we had guests at some of the resorts that were unable to check into their rooms because we had a massive broadcast storm going on the network. And after we determined that's what was going on, we temporarily broke the loop. We unplugged one of the redundant connections from our Cisco Catalyst switch. And then later somebody came and replaced hardware. And I want you to know what to look for if you suspect that you have an STP failure. Let's take a look at some symptoms of a Spanning Tree Protocol failure. One thing is MAC address table corruption. Consider PCA on screen. Let's say that it has a MAC address of all A's. And when it sends a frame out on this segment, that frame goes into the top ports of switches A and B, and they populate their MAC address table. They say that the all A's MAC address lives off of gigabit 1/0/1. And then the frame gets forwarded down to the bottom segment, going down to PCB. But notice that PCB received duplicate frames. The frame was forwarded by switch A, and a duplicate frame was forwarded by switch B. And what's maybe worse than that is the frame from switch A was seen on switch B's bottom port, and the frame from switch B was seen on switch A's bottom port. And they independently concluded that, oh, I must have been mistaken. It looks like the all A's MAC address doesn't live on the top port, it lives on the bottom port. And that's incorrect. We now have MAC address table corruption. Another issue, the issue that I experienced at Disney that I was telling you about, is a broadcast storm. If PCA were to send a broadcast out on this network, it gets flooded into the top port of both switches, and they flood it at their bottom ports, and then the broadcast from switch B goes into switch A, and the broadcast from switch A goes into switch B. It just loops infinitely, unlike a routing loop, where we have a time to live value that can expire. There is no time to live value in a frame header. It just circulates endlessly, and we can have some serious performance issues on the network if we get into a broadcast storm. And if you experience issues like that, you may have a Spanning Tree failure. And a temporary way to possibly fix that is to disconnect one of the physical links. And then you might need to come back and replace hardware on the device where Spanning Tree has failed during a time to minimize impact on your end users. That's one thing that could happen with Spanning Tree Protocol. We could have a failure of the Spanning Tree Protocol. Something else that could happen, much more common, is to have a suboptimal path. If you just happen to have several Cisco Catalyst switches, maybe some of them are new, some of them are old, and you just interconnect them, Spanning Tree is going to happen. Spanning Tree will dynamically determine who is the root bridge, that point in the tree back to which all of the other switches point. And it might not be an optimal root bridge. You might not be taking an optimal path to get from one switch to the other switch. It's important that we be able to look at a topology and determine who is the root bridge and what are the roles of the ports in this topology. And Cisco does us a huge favor. They allow us to run a flavor of Spanning Tree Protocol called PVST+. Per VLAN Spanning Tree Protocol Plus. With PVST Plus, we're able to have a different instance of Spanning Tree running for different VLANs. Maybe one Spanning Tree would be optimal for VLAN 100, but another Spanning Tree, another topology with a different root bridge and different ports blocking and different ports forwarding, maybe that would be optimal for VLAN 200. And we can have different Spanning Tree instances for our different VLANs. And if you have lots of VLANs, maybe you don't want to run an instance of Spanning Tree Protocol for each and every VLAN. Well, Cisco allows us to do something called MSTP. We can run multiple Spanning Trees Protocol. With multiple Spanning Trees Protocol, which by the way is sometimes written as MST for multiple Spanning Tree Protocol, if we're running that, we can define instances of Spanning Tree. We can define an instance that says this switch is the root, and we can define another instance to say this other switch is the root. Maybe we have 20 VLANs, but we've only defined three instances of spanning tree. We can put VLANs that need the same spanning tree topology in the same instance. And another group of VLANs that would benefit from the same spanning tree topology, we associate them with another instance. So MSTP, or MST if you prefer, that's a way for us to still have optimal pathing for our different VLANs while not having to have an instance of spanning tree protocol running for all of our VLANs. But regardless of which version of spanning tree we might be running, a critical skill for us to have is to be able to look at a topology and determine who is the root bridge. And what are the various port roles? Which ports are forwarding? Which ports are blocking? Let's go through an exercise, a little bit of review for us, to identify the different port states. And let's identify the root bridge to begin with. Remember that the root bridge is the bridge in the topology, or the switch in the topology, with the lowest bridge ID, the lowest bid. And the bid is a combination of a priority, the switch's priority, and the MAC address of the switch. If you just take a Cisco Catalyst switch out of the box, it's going to have a priority, a bridge priority, of 32,768. Meaning if you just interconnect a bunch of switches and you leave their priorities at their default values, they all equal. And that means the MAC address is the tiebreaker. The lowest bid, the lowest bridge ID becomes the root bridge. And if we're all set at the default priority, that means the lowest MAC address is going to become the root bridge. Well, take a look at this topology on screen. Who has the lowest bid? Well, the priorities are equal. They're at the default settings. So we look to see who has the lowest MAC address. And 000, the first three hexadecimal digits in the MAC address for switch B, that's less than 001 on switch A. Switch B, therefore, is our root bridge. Once we've determined the root bridge, now we want to determine the roles of the various ports, which ports are forwarding and blocking. And the first type of port is a root port. And the definition for that is it's the port on a non-root bridge that's closest to the root in terms of cost. Notice it says a non-root bridge. A root bridge doesn't have any root ports. We only have root ports on non-root bridges. And it's closest to the root bridge in terms of cost. And by default, cost is going to be calculated as a factor of bandwidth. Notice in this topology on screen, we're running at 100 megabits per second on that top segment, and we're running at 10 megabits per second on the bottom segment. And I've given you a table to show you the costs associated with various speeds. A 100 megabit per second link, that's going to have a cost of 19. A 10 megabit per second link, that's going to have a cost of 100. Therefore, from the perspective of switch A, it's a cost of 19 to get back to the root bridge over the top link. It's a cost of 100 if we use the bottom link. Therefore, Fast Ethernet 1/0/1 on switch A, that's our root port. Now we say, what are the designated ports? And every segment has a designated port. And it's the one port on a segment that is closest to the root in terms of cost. And here we only have two segments, one on the top, one on the bottom. And you don't get closer to the root than being on the root. And therefore, both of the ports on the root bridge are designated ports for those two segments. The end of the segments that are closest to the root bridge are actually on the root bridge. Those two ports on switch B, those are designated ports. What's left over? Well, we've got Fast Ethernet 1/0/2 on switch A. Assuming it's not administratively down, it's not disabled in other words, then it's going to be a non-designated port. It's going to be blocking. And let's take a moment now and go out to a live interface and see if we can determine who is the root bridge. Which ports are blocking? Which ports are forwarding? Let's go out to a live interface now and check it out. Let's see if we can analyze spanning tree for this topology we see on screen. And we're running PVST+, meaning that each VLAN has its own spanning tree protocol instance. Let's say that we're concerned right now with VLAN 100. I can say on each of my switches, show spanning-tree for VLAN 100. And on switch SW1, we see that the root has a priority of 32,868. By the way, you might remember that the default priority was 32,768. Well, this priority, because we're running PVST+, is calculated by adding the VLAN ID to the bridge priority. We've added 100 to 32,768 to give us 32,868. That's the reason that this number is a bit larger than the 32,768 we were talking about earlier. But this is the priority of the root. This is our priority. The priority is equal. However, the root has this MAC address, and we've got this MAC address. We're not the root. The root has a lower MAC address than we do. We can see that the root port is Fast Ethernet 1/0/13, and we can see that I'm blocking on Fast Ethernet 1/0/14. That means if I'm trying to get down to a member of VLAN 100 connected off of switch SW3, I'm not going to be using this link to go directly to SW3 because that link is blocking right now. Instead, I'm going to have to go down to switch SW2, and SW2 will then forward the traffic over to SW3, and that may or may not be optimal depending on our traffic patterns. Maybe for VLAN 100 it would be better if switch SW1 were the root, but currently we're not the root. Let's see if we can find the root though. Let's go to SW2 and let's do a show spanning-tree VLAN 100, and it says very clearly this bridge is the root. We are the root, and as a result, all of our ports are designated ports. Remember, a designated port is the port on a segment that's closest to the root in terms of cost, and we don't get closer to the root than actually being on the root, and we're all designated here. Let's go to SW3 and do a show spanning-tree VLAN 100 command, and we can see that I've got a root port connecting over to switch SW2 on Fast Ethernet 0/1, and I've got another path that would also get me to SW2 over a Fast Ethernet 0/2, but it's blocking right now because that would be a loop if I were allowing that port to be forwarding right now. I am forwarding, by the way, going up to SW1, which might be surprising to you because the other end of this link on SW1 was blocking. Remember that? We were blocking from SW1 coming down to SW3. Let's just review that. On SW1, we said this port that goes down to SW3, it was blocking. So how come SW3 says, no, we're forwarding on that link? Well, on a segment, you're not going to have two ports that are blocking. You might have one port that's a designated port and the other port is blocking, but they're not both going to be blocking. What makes this the designated port is that this is the port that is considered to be closest to the root in terms of cost. If we look at the ports on each end of that link between SW1 and SW3. And now we've taken a look at our topology. We've determined that SW2 is the root. We've seen which ports are blocking, which ports are forwarding. We've identified root and designated ports. But let's imagine that we want to manipulate this. Let's say for VLAN 100, it would be more optimal for switch SW1 to be the root. Here's how we could fix that. Let's go to SW1, and in global configuration mode, we can say spanning-tree VLAN 100 root, and I could say I want this to be the primary root for this VLAN, or maybe I designate another switch as the primary and I say I want this to be the secondary. So if the primary root goes down, then the secondary root can take over. But I'm just going to say I want this to be the primary root for VLAN 100. And now that we've done that, in the background, Cisco IOS has manipulated the bridge priority of switch SW1 to make it the root. Let's see what it looks like now if I do a show spanning-tree VLAN 100. Now it says this bridge is the root. You see how Cisco IOS automatically reduced the bridge priority to make it the root, and as a result, both of our ports are now designated ports because we are the root bridge. That's a look at how we can interrogate an actual topology to determine who's the root, who's forwarding, who's blocking, and how we can manipulate who the root bridge is for a particular VLAN. But another spanning tree protocol issue that we might have is there's a failure that happens, and spanning tree takes a long time to converge. Let's talk about suboptimal convergence. Let's say that we had a link failure in our spanning tree topology, and a port that was blocking transitioned to forwarding. With regular PVST+, that's going to take on the order of 50 seconds. Remember that we stay in blocking for 20 seconds, waiting for those BPDUs to come from the root, and when they don't come, then we transition into listening for 15 seconds. We're listening to the BPDUs, we're learning our place in the network, then we transition to learning. We're starting to populate our MAC address table, and then after a grand total of 50 seconds, 20 plus 15 plus 15, we finally go to forwarding. That seems a little bit long. Or let's say that I plug a laptop into a switch port. It wasn't blocking to start with, so we don't have to wait 50 seconds, but still, we might have to wait 30 seconds. We don't have to remain in blocking because we were not in blocking to start with, but we still have to go through the 15 seconds of listening and the 15 seconds of learning for a 30-second delay. And a lot of laptops today, they've got those solid-state drives. They can boot up really quickly. Your laptop might boot up and try to get an IP address using DHCP, and it fails because the port into which you're connected hasn't gone active yet. We want to speed up these STP convergence times if we can. We don't want to have suboptimal convergence. And we've got some features that can help us out. Well, I guess the biggest feature is a different flavor of spanning tree protocol. There's something called 802.1W, or rapid spanning tree protocol. And depending on your topology, depending on how big it is, and depending on where the failure occurs, you can have much quicker convergence than 50 seconds. It could be on the order of 1 to 3 seconds. Again, that can vary, but it's going to be a lot faster typically than regular spanning tree protocol. By the way, Cisco's implementation of rapid spanning tree protocol allows us to do rapid PVST+, where each VLAN can have its own instance of rapid spanning tree protocol running. Now let's take a look at some features that can help reduce the convergence time of STP. We don't need this first one, uplink fast, if we're running rapid spanning tree protocol, because it's got a feature similar to this. We also do not need backbone fast if we're running rapid spanning tree protocol. It's got a feature similar to this, but these features can be useful if we're running PVST+, for example. But port fast can help us in any of our flavors of spanning tree protocol. Port fast allows us to plug a laptop into a switch and not have to wait for 15 seconds of listening and the 15 seconds of learning. We can say, I want this port to go active almost immediately as soon as something connects. Let's take a closer look at some of these features that can help reduce STP convergence time, beginning with uplink fast. Uplink fast is typically going to be configured on access layer switches. We would not want to enable it on a transit switch. We don't want to enable it on SW2 on screen. You see, SW2 is a transit switch. We flow through SW2 as we're going from SW1 to SW4. Or same thing with SW3. That would be another transit switch, but we might configure it on SW4. And when we configure it, it's not on a port-by-port basis. We enable it globally. And uplink fast can help us reduce convergence time if we have a direct link failure. Let's say that we have a link failure between SW2 and SW4. That link goes down. And when that happens, this port that had been blocking, we know that it was blocking because it's another way to get back to the root. So SW4 almost immediately transitions that to a root port. And now SW4 knows how to get back to the root bridge. We still have an issue though, and that is the other switches in the topology, SW2, SW3, they learned how to get to the devices hanging off of SW4 with the MAC address of all A's and the MAC address of all B's. They knew that they would go to SW2, and then SW2 would forward the traffic down to SW4. Now they need to go via SW3. We need to re-educate the switches about the best way to get to these MAC addresses. And to re-educate those switches very quickly, we can send out some dummy multicast frames. Now, I call them dummy multicast frames because they don't contain any meaningful data, but they are multicast frames that have the source MAC addresses of the devices connected off of SW4. It's a way for the other switches in the topology to repopulate their MAC address table with updated information. Here's how we can set up uplink fast. Remember we said it was going to be configured globally? What we're going to do is to go into global configuration mode and we can say spanning-tree uplink fast. And we can verify it by doing a show spanning-tree uplink fast, and we can see whether or not it is enabled. Next up is backbone fast. Backbone fast can help us with an indirect link failure, and we typically configure this on all of the switches in the topology. And it again is globally enabled on the switch. And while uplink fast helped us when we had a direct link failure, backbone fast can help us when we have an indirect link failure. For example, on screen, SW3 is about to react to an indirect link failure. Let's say that we have a link failure between SW1 and SW2. It's not directly connected to SW3, but here's what happens. When that link fails, this causes SW2 to think it's now the root. And SW2 is going to send out a BPDU claiming to be the root. It says, I am the root. But this is an inferior bridge protocol data unit. In other words, the bridge ID is greater than the bridge ID of the actual root bridge of SW1. Well, when SW3 sees that inferior BPDU, if we were not using backbone fast, switch SW3 would just ignore it and say, oh, that's an inferior BPDU, and we would have to wait the 50 seconds for that blocking port to start forwarding. But if we have backbone fast enabled, SW3 is a bit more proactive. It's going to send a query up to the root bridge, And it's going to say, hey, I'm just checking. Do I still have a path to you, Mr. Root? It sends up an RLQ, a root link query, and the root bridge says, why, yes, you do. It sends a root link query reply, and it says, yes, this is the way to get to me. I am the root bridge. When SW3 gets that, it realizes that SW2 is having delusions of grandeur, and it sends it another BPDU to say, I just wanted to let you know that you're not really the root. SW1 is the root bridge, and here's its BPDU to prove it. You see, it's got a superior BPDU than you have. And Switch SW2 says, oh, how embarrassing. Thank you for telling me. I'm now going to transition my port to a root port instead of a designated port, and we'll get back to the root by way of Switch SW3. Here's how we set it up. We do set it up globally again. We go into global configuration mode, and we can say spanning-tree backbone fast. It's that easy. And to confirm that it's on, we can say show spanning-tree backbone fast, and it tells us whether or not it's enabled. Again, uplink fast, backbone fast, not needed with rapid spanning tree protocol, because rapid spanning tree protocol has features that can do similar things, but even rapid spanning tree protocol can benefit from port fast. With port fast, we can configure this on ports connecting out to an end station in our network. And we can configure it globally, or we can do it on a port-by-port basis. If we turn it on globally, it's going to apply this feature to all non-trunking ports. And this is going to allow a switch port to go active almost immediately when we connect a device into that switch port. For example, I've got a laptop on screen, and I'm going to connect it into Fast Ethernet 1/0/1, and when I do, that port almost immediately goes active. We don't have to wait for 15 seconds of listening and 15 seconds of learning, which might prevent that laptop from getting an IP address via DHCP. Here's how we set it up, both globally and at the port level. If we want to set it up at the port level, we go into interface configuration mode, let's say for Fast Ethernet 1/0/1, and we can say spanning-tree port fast. It's that easy. If we want to turn it on globally, in global configuration mode, we would say spanning-tree port fast default, and that turns it on all of the ports that are not trunking ports. And if we want to see if port fast is enabled for a specific port, we could say show spanning-tree interface, followed by the interface identifier, followed by port fast. And here it says, yep, for VLAN 300, this interface is enabled for port fast. And that's a collection of STP tools that can help reduce convergence time. But there's another issue that we might run into when we're troubleshooting spanning tree protocol, and that's instability of our spanning tree. Maybe we have somebody accidentally or intentionally add a switch to the topology, and it has a lower bridge ID. It becomes the root. Maybe we don't want it to become the root. Suddenly we have a suboptimal path again. What features do we have that can help increase the stability? Let's take a look. And these features can be useful on rapid spanning tree protocol as well. We mentioned that a couple of the other features, uplink fast, backbone fast, we didn't really need them for rapid spanning tree protocol. These we can use with rapid spanning tree protocol. First is BPDU guard. There's BPDU filter. There is root guard. And finally, there is loop guard. Let's talk about each one of these, beginning with BPDU guard. BPDU guard is often used with port fast because a port enabled for port fast should not be receiving BPDUs, obviously. And even though port fast does have its own loop prevention mechanism, that loop prevention doesn't happen instantly. We can have a brief period of time where we have a loop. And BPDU guard can help prevent that temporary loop by placing a port into an error-disabled state if a BPDU is seen on that port. And we can enable it on a port-by-port basis, or we can enable it globally. If we enable it globally, it's applied to ports that have port fast enabled. And like we said, what it does, if we see a BPDU on this port that's enabled for port fast, we're going to go into an error disabled state if we see a BPDU. For example, if I've got a PC plugged into switch SW4 and I've got port fast enabled on Fast Ethernet 1/0/1, everything is happy, but let's say that that laptop gets taken home and somebody comes along with a switch and thinks, yeah, I need to plug this switch in somewhere. And we plug it into this port that's enabled for port fast. And switch SW5, it will send a BPDU, and when that's seen by switch SW4, it says, oh, no, you don't. I'm going to go into an error disable state because I'm receiving a BPDU on a port that's enabled for port fast. Here's how we set it up. What we can do is go into interface configuration mode to set this up at the interface level. Let's say we're going into interface fast Ethernet 1/0/1, and we can say spanning -tree BPDU guard enable. If we want to set it up globally, where it's going to be applied to ports with port fast enabled, we would say spanning -tree port fast BPDU guard default. And we can see if it's running for our instance of spanning tree by saying show spanning -tree summary. And you can see that about 4 lines up from the bottom, it tells us that BPDU guard is enabled. The next feature that can help improve our stability of STP is a BPDU filter. What this does is prevent a port from sending BPDUs. Normally, we like BPDUs to be exchanged between our switches, but BPDU filter can prevent a port from sending BPDUs. We can enable this on a port-by-port basis, or globally where it applies to ports that have port fast enabled. Now, we should be careful with this feature and only use it when necessary. So when would something like this be necessary? Well, one example is when we're interconnecting autonomous systems, and we're interconnecting those different networks under different administrative control with a layer 2 link. We might not want to exchange BPDUs between these different autonomous systems. And we can configure this at the port level or globally, but if we configure this at the port level, it's most dangerous. Let me explain why. If we configure this at the port level, we're telling the port, do not send any BPDUs, and if you receive any BPDUs, ignore them. This could be dangerous because we're ignoring incoming information. If we enable a BPDU filter globally, though, the switch says, if I receive a BPDU on a port fast port, that port is going to lose its port fast status. Cisco considers that to be a safer approach. But you might have an occasion in your topology to say, yes, I want to filter BPDUs flowing between maybe different autonomous systems. For example, switch C, if it tries to send a BPDU down to switch D, it's going to be suppressed because we've applied a BPDU filter to switch C. Here's how we can set it up. Remember, we can set it up at the port level, which is considered the most dangerous, or globally. Let's see first how to do it at the port level. We could go into interface configuration mode for fast Ethernet 1/0/1, and we can say spanning -tree BPDU filter enable. If we want to enable this globally, we say spanning -tree port fast BPDU filter default. And we can see if it's on by saying show spanning -tree interface fast Ethernet 1/0/1 in this example, followed by the keyword of detail. And you see a couple of lines up from the bottom, it says for that interface, BPDU filter is enabled. Our next feature is root guard. Root guard prevents a situation where someone might maliciously or accidentally add a switch to the network, and that switch becomes the root. And we would typically configure this on ports off of which a root bridge is not expected. For example, switch SW3 on screen, it's not the root. We don't want it to be the root. SW1 is configured as the primary root, SW2 is configured as the secondary root. We don't want SW3 to be the root. So on the bottom ports of SW1 and SW2, we can enable root guard, and ports enabled for root guard will enter a root inconsistent state if they start receiving superior BPDUs. If switch SW3 were to start sending BPDUs that say, I am the root, and sure enough, the bid is more attractive than the real root. It's a superior BPDU. Even though it's superior, we're not going to listen to it. Switch SW1 would say in this case, I received a superior BPDU, but it's off of a port on which I do not expect to see the root. What I'm going to do is go into a root inconsistent state, and this port is going to stay in that state until I stop receiving BPDUs off of that port. Here's how we can set it up. We only configure this, by the way, at the port level. Let's go into interface configuration mode, let's say for fast Ethernet 1/0/2, and we can say spanning -tree guard root. And to see if we do have any ports that are in that port inconsistent state, we can say show spanning -tree inconsistent ports, and it looks like we do have one here. And the final feature that can help with our spanning tree protocol stability is loop guard. This is a feature that we might want to use in conjunction with root guard. It causes a blocking port, like a non-designated port, to enter a loop inconsistent state if it stops receiving BPDUs. You see, normally on a network segment, a designated port is going to be sending out BPDUs, and we might have a non-designated port at the other end of that segment, and it's going to be receiving those BPDUs. However, if the non-designated port stops receiving BPDUs, it assumes that this topology must be loop-free, and I'm going to start transitioning to the forwarding state. But maybe it stopped receiving BPDUs, not because we truly have a loop-free topology, but because we have a unidirectional link as an example. This could create a one-way loop around the topology because we're sending BPDUs even though we're not receiving them. Now, we can enable this on a port-by-port basis. Typically, we would do this on ports not configured for root guard, or we could enable it globally where it would be applied to all point-to-point links. You may have heard the term in the industry backhoe fade. We give that name to a situation where we might have some digging going on in the environment, and we might have a backhoe that damages a fiber optic cable. Maybe it severs one of the fibers in a fiber pair. SW3 might say, I'm no longer receiving BPDUs. Does that mean that the topology is loop-free? No, just because SW3 is not receiving BPDUs, that's no guarantee that it's not sending BPDUs. We don't want to have a one-way loop. The great news is SW3 has that port, Fast Ethernet 1/0/2, enabled for loop guard. And since it stopped receiving BPDUs, instead of going into a forwarding state, it goes into a loop inconsistent state. Here's how we can set this up. Let's go into interface configuration mode to see how to set this up at the port level first. We're going into interface Fast Ethernet 1/0/1, and to turn this on, we simply say spanning-tree guard loop. If we want to turn it on globally, we can say spanning-tree loop guard default, and to see if it is turned on, we can say show spanning-tree summary, and you can see a couple of lines up from the bottom that globally loop guard is enabled. And that's a look at some issues we could have with a spanning tree protocol in our network. We might have a hardware failure, which might be evidenced by things like MAC address table corruption or a broadcast storm. We might have a suboptimal path, and those paths or the spanning tree topology might need to be different for different VLANs, and we can set that up. We might have suboptimal convergence times. It might be taking 50 seconds for a port to transition from blocking to forwarding, and we talked about how we could speed that up a bit. Or we might have some instability in our spanning tree, where somebody introduces a switch and it becomes the root, and we don't want it to become the root. Or maybe we have a unidirectional link failure, and that causes a loop. And we talked about some safeguards that could help stabilize our spanning tree topology.